Hi everyone, welcome to our video example here, and this is related to our lecture where we talked about using tables of values to look up specific enthalpies or specific internal energies. This is question 7.33 from your textbook on page 391. Flip open your textbook, read this question first, and then follow along with this video example. So in this example, we have superheated steam at 40 bar absolute and 500 degrees C. We are given the mass flow rate of 250 kilograms per minute into an adiabatic turbine. So adiabatic means there is no heat transferred to and from the system, where it's expanded to 5 bar. The turbine develops 1500 kilowatts of energy. Once it gets out of the turbine, the steam flows to a heater where the steam is now reheated back up to its initial temperature. So we're going back up to 500 degrees C. We're told to neglect kinetic energy changes. So there are 4 different parts to this question. The first 3 parts is really looking at each system and then the overall system. For part A, we are asked to write the energy balance on the turbine. For part B, we're supposed to do the energy balance on the heater. And then for part C, we're going to do it for the overall system and verify that it is essentially consistent with the fact that we have a turbine and a heater, and the sum of that should give us our overall. And the last part, we have always assumed that the kinetic energy, the change in kinetic energy is negligible. And in part D, we'll actually show that it is negligible compared to our other terms in our energy balance. All right, so this is a really simple one in, one out system for both the turbine and the heater. So I'm not going to go through the details of drawing the diagram and actually labeling it. Here is the diagram. We have our turbine and our heater. We are given the temperatures and pressures and the mass flow rate coming into the turbine. It is an adiabatic turbine, so our Q is 0. We know that work is done by the system to spin this turbine, and so we have a shaft work of negative 1500 kilowatts. We have the steam coming out in stream 2. We are only given the pressure. Eventually, we want to find the temperature, and that's using part A. We have the mass flow rate there. All this goes into the heater. In this case, it's just a reheater, so there's no shaft work. We know the shaft work is going to be 0. We're given that the outlet conditions, the pressure stays the same, temperature goes back up to 500 degrees C, and so we want to use that to find Q. So that's our diagram. Let's go through each part individually. Let's start with A. So now we are looking only at the turbine as our system. We're going to write the overall energy balance, figure out which terms are 0, and then expand it back out. So before we get there, we have our mass flow rates. We know the mass flow rate coming into the turbine is 250 kilograms per minute, but it's a simple one in and one out across the entire system. So we know that M1 is just equals to M2 equals to M3, and it's just equals to some generic M, and they are all 250 kilograms per minute. All right, now we have that out of the way, we can actually focus on our energy balance. Let's start with that. We have our energy balance around the turbine. This is the overall this is the open system energy balance. We know that Q is 0 because it's an adiabatic turbine. We're going to assume no kinetic energy changes, and we're going to assume that the pipes are coming in at the same elevation, so no potential energy changes. So those 3 are going to be 0, which means we're going to have delta H equals to the shaft work. And now let's expand out our delta H. The delta H is all the outputs minus all the inputs. In this case, there's only one output and one input. So writing it in terms of specific enthalpies, it is the mass flow rate of the outlet stream times the specific enthalpy of the outlet stream minus that product of the inlet stream. And that's expanding out the delta H, and that's equals to Ws. All right, if we look at this, we know that M2 is equals to M1. So eventually we'll just use a common M for this, like we said, for the, from the simple mass balance. We know everything down here, and we know this is a superheated steam, which means we can look up that value from table B7. So go ahead and look up table B7 for 500 degrees C and 40 bar and verify that you can get 3445 kilojoules per kilogram. With that, what we can actually do is solve for our H2 down here, because that will allow us to eventually figure out our T2. So rearranging the equation to calculate H2, we put in all the numbers, and what I essentially did down here as I put in all the numbers is just making sure the units are consistent. Our H hat 1 is in kilojoules per kilogram, so I want to make sure that when I do my shaft work over the mass flow rate, I end up with kilojoules per kilogram. And now I have my H2 as 3085 kilojoules per kilogram. So how are we going to find temperature in this case? We're going to use table B7 in a kind of backwards fashion than what we are used to. We're used to be given the temperature and pressure, and we look up the value. Now we have the value. We're going to figure out what temperature that is at. So here's the table. We're going to use linear interpolation because it's not going to fall exactly where we need it to be. We are at 5 bar, so that's the row we're going to look at. And we are at 3085. So looking at this table, we see that at 300 degrees C we have 3065, and 350 degrees C we have 3168. So we know that our temperature is going to be somewhere between 300 and 350. We're going to use linear interpolation. We have done some linear interpolation in the past, but let's review what that is. What we are saying is that between 300 and 350 degrees C, we have these two enthalpy values, and all we can assume is that the trend between it is a straight line. So there's a couple of ways you can do this in terms of linear interpolation. What we're trying to find is at 3085 specific enthalpy, what is the temperature? You could use our two data points and figure out an equation for this line and then plug in the h hat of 3085. Or the easier way is to just do it by ratios. Because this is a straight line, we know that the ratio of this height over this height is equals to the ratio of this length over this length. And that's just simply because we have a linear relation. So if we just write that, the left-hand side is the length on the x-axis, T2 minus 300 over the entire length, is equals to 3085 minus 3065 over the entire height over there. With that, I can calculate T2 right away, and so we can estimate T2 as 309.7 degrees C. All right, so that's part A. We are able to solve for our temperature in our stream 2. Let's go on to part B. Now we're moving on from the turbine to the heater. We're going to do the same thing. Now we're going to look at the energy balance for the heater. So starting with our overall and our generic energy balance for open system. No kinetic energy changes, no potential energy changes. In this case, no shaft work. So those three terms are going to be 0. Expanding out our delta H again, that is going to be the mass flow rate in 3 multiplied by the enthalpy in 3 minus that in stream 2. So we can write that, but in this case, you realize that we already have h hat 2 from the part A. We already found that. We can look this up, 500 degrees C and 5 bar. So go back to table B7 and look that up. We know the mass flow rates M3 and M2 are just 250 kilograms per minute, so we can calculate our Q. So from table B7, we see that H3 is 3484 kilojoules per kilogram at 500 degrees C and 5 bar. Put everything into our equation, and we end up with a heat transfer of 99,750 kilojoules per minute. But let's make it consistent and do everything in kilowatts, and this asks for the question. So kilowatts is kilojoules per second. Converting that, we get 1662.5 kilowatts. So we have an energy balance for the turbine, we have an energy balance for the heater. Now we're going to look at the overall energy balance for this entire system, and it should be consistent with what we found from the turbine and the heater. And that's what question part C is asking for. Now we're looking at the overall, which means we are looking at stream 1 versus stream 3, but at the same time we have both heat input and shaft work. So the shaft work is from the turbine and the heat is from the heater. The overall energy balance again, no kinetic energy changes, no potential energy changes. We do have Q, we do have shaft work. So those are the only terms that are 0. And now let's look at the left-hand side, which is our delta H. Expanding it out again, it is the output stream minus the input stream. The output stream is stream 3 in this case, and the input stream is stream 1. We already have all the H hat values from the previous parts. So now we're just going to put it all in, and we see that the delta H for this entire process is 162.5 kilowatts. In terms of the right-hand side, we have Q plus WS. Q comes from the heater, and we know that that was 1662.5. That was our part B. And we know that shaft work was minus 1,500 kilowatts. That was given a question for part A. If we put it all together, you can see that it is 662.5 kilowatts. We see that left-hand side is indeed equals to the right-hand side, so the overall balance is satisfied, which should be the case. All right, so now we have looked at the energy balances for each of the individual systems. What we want to do is to go back and question our assumption that kinetic energy changes are actually negligible. Right. To do so, we actually need to assume some pipe diameter, as you can see why as we go through the question. In this case, we are told that the diameter is going to be 0.5 meters. Let's expand out the kinetic energy, changing kinetic energy term for the turbine. So we have half mu squared for the outlet minus half mu squared for the inlet. We're going to replace our velocity. How is velocity related to flow rate? It is your volumetric flow rate over the cross-sectional area of the pipe it is flowing in. So M2 is V2 over A, M1 is V1 over A, so I did that replacement in there. And now I'm just going to simplify it further. Since the cross-sectional area is the same, I'm going to pull out the A squared, and there I have my expression here. What we now need is our volumetric flow rates in stream 2 and stream 1. What we have is mass flow rate. How do we convert from mass to volume? We will use density, but because this is a gas, going back to chapter 5, what we can do is use some equation of state to relate that. If we make the ideal gas assumption, we can use the ideal gas law. So that would be the way that we would have done it back in chapter 5. But now you realize that in this table, we have one more piece of information that we had not used. In addition to U hat and H hat, we are also given V hat. And V hat is essentially our 1 over our density. So we're just going to look up our V hats. In terms of V1, we have at 500 degrees C and 40 bar, go back to table B7, look up the V hat value, and you have 0.0864 meters cubed per kilogram. This is essentially 1 over the density of this gas at this temperature and pressure, of this steam at this temperature and pressure. So we have that. We can convert from our M1 to our V1 by just multiplying our M1 with our V hat 1. You can verify that equation is true by using the units. I'm going to convert everything to SI units. So now I have meters cubed per second. We see that the volumetric flow rate in going into the turbine is 0.36 meters cubed per second. With V2, just like we did with temperature, we need to use linear interpolation. I'm not going to go through the entire process again, but verify that these are the numbers that you can find from table B7. From there, I can solve for my V2. Use the same idea, multiply my V hat 2 with my M2. Now I have my volumetric flow rate coming out of the turbine. Now we have all the values that we need to put it back into our changing kinetic energy term, half mu squared term. Recall that was the equation that we simplified from before. We have everything. We have the cross-sectional area of the pipe because we know the diameter of the pipe. We have the mass flow rate. We now have the volumetric flow rates. As long as I keep everything in SI units, which is what I'm doing down here, I know my answer is going to drop out in SI units, so I'm going to have joules per second or watts. And I end up with 258.1 watts. In kilowatts, it will be 0.258 kilowatts. If you recall, our Q and our W is on the order of 1,000 kilowatts. So we're looking at an order of magnitude about 4 to 5 smaller than our Q and WS. And that's why, because of that, you can see that why our kinetic energy term is actually negligible, and we can choose to neglect that because it's so much smaller than the rest of our other terms. So that's all we have for this example. There's one more example where we're going to put it actually into a proper material balance problem. In this case, in this problem, you see that our material balance is actually rather simple. It's just a simple 1 in, 1 out. We're going to put it into our actual material balance problem, and that will be our second video example. So work hard, be smart. I'll see you then.